In the previous class, we derived the equation for the electric field intensity in the lossy dielectric medium. We discussed the equation of the electric field intensity in the lossy medium in phasor as well as instantaneous form. So this is the phasor value of the electric field intensity in lossy medium, and here is the instantaneous value of the electric field intensity in a lossy dielectric medium. Electric field intensity is a vector quantity, and we know that a vector quantity has a magnitude as well as direction. So the direction of this vector quantity is given by the unit vector ax. We assume that this vector is in the direction of the unit vector ax. So we derived this equation in the previous class, and today we are going to discuss the angular frequency of the electromagnetic wave, which is represented by omega, the phase constant of the wave, which is represented by k, and the speed of the wave or the velocity of the wave, which is represented by v. So we are going to discuss these three electrical quantities. We shall derive the equation for all these three electrical quantities in this class, and then we are going to discuss the Beer's law. Okay, so we will discuss these quantities in this particular class. We know that the electric field intensity is a vector quantity. This vector quantity has a magnitude as well as a proper direction. So we are going to consider the magnitude of the electric field intensity only. And here is the magnitude of the electric field intensity. The magnitude of the electric field intensity is equal to E naught into sine of omega t minus kz. So let us consider this equation once again. You see, we consider the magnitude of the electric field intensity in equation number 8.49. And if we focus on this equation, the electric field intensity changes with time as well as distance. You see, the electric field intensity changes with time as well as distance. The electric field intensity changes with respect to t as well as distance, that is z. So we are going to study the variation in the magnitude of the electric field intensity with respect to time only. If you want to study the variation in the electric field intensity with respect to time, then we will assume that z in this particular equation is 0. And if z is 0, then definitely kz, we will represent this quantity by kz. So kz will be 0 as well. Okay. So if kz in this equation is equal to 0, then this equation can be written in the form of equation number 8.50. You see, this is the magnitude of the electric field intensity, which is varying sinusoidally with respect to time. So the magnitude of the electric field intensity will be equal to E naught into sine of omega t. So what we do, we plot the magnitude of the electric field intensity with respect to omega t. We take omega t along x-axis and the magnitude of the electric field intensity along y-axis, and we get the sine wave form as shown in this figure number 8.3. So we can say that the magnitude of the electric field intensity varies sinusoidally with respect to time. You see, the time taken by one complete cycle of the wave is known as time period. And time period is represented by capital T. We want to find out the equation for the angular frequency, which is represented by omega, and the unit of the angular frequency is radian per second. So let us consider point P over here. Okay. So what we do, we consider point P, and we know that at the given point, at point P, the value of omega t is 2 pi. So let me consider this diagram once again. If we consider this point P, where is the diagram? Let me show it once again. If we consider this point P, the value of omega t at this particular point is 2 pi. Okay. And the value of small t is equal to capital T. So anyhow, what we do, we consider this point P, and the value of omega t at this particular point is 2 pi. So we know that at point P, the value of t is equal to capital T, which is the time period. So we put the value of small t in this particular equation, and we get omega t, which is equal to 2 pi. And omega will be equal to 2 pi by t. And we know that the reciprocal of the time period is known as frequency. In other words, the number of cycles per second is known as frequency. So the frequency is represented by small f. So if we replace f by 1 over t, then omega will be equal to 2 pi f. This is how we calculate the angular frequency of an electromagnetic wave in any medium. So the angular frequency of an electromagnetic wave in any medium will be equal to 2 pi f. This equation is valid in any medium. We don't care whether the medium is a lossy medium or a lossless medium. So what we do, we are going to derive the equation for the phase constant now. Well, the phase constant is represented by k. And we know that k is basically equal to omega under root mu epsilon. We can calculate k with the help of this particular equation as well, where omega is the angular frequency of the electromagnetic wave, which is equal to 2 pi f. So if omega is known, the permeability of the medium is known, the permittivity of the medium is known, we can calculate the propagation constant or the phase constant with the help of this equation. So this is one way to find out the propagation constant of the electromagnetic wave in any medium. Well, K depends upon the medium as well, because K is a function of the permeability of the medium and the permittivity of the medium. So it depends on the properties of the medium, right? So anyhow, this is equation number 1. We can calculate the propagation constant K with the help of equation number 1. Let me write down equation number 1 once again. K is equal to omega under root mu epsilon. Okay, so we can calculate the propagation constant with the help of equation number 1, but we are going to derive another equation for K in this class as well. So let us consider the phase constant of the transverse electromagnetic wave in a dielectric medium. Okay, so once again we consider the magnitude of the electric field intensity in a lossless dielectric medium, which is given by equation number 8.51. So here is the magnitude of the electric field intensity in a lossless dielectric medium, and the magnitude of the electric field intensity is changing with respect to time as well as distance. So the magnitude of the electric field intensity is changing with respect to distance as well as time. We have studied the variation in the magnitude of the electric field intensity with respect to time. Now let us study the variation in the electric field intensity with respect to distance. So if you want to study the variation in the magnitude of the electric field intensity with respect to distance, we assume that omega t is equal to pi radian. So we replace omega t in the previous clause by pi radian. So if omega t is pi radian, then the electric field intensity will be equal to E naught into sine of pi minus k z. Okay, so this will be the equation for the electric field intensity of the electromagnetic wave with respect to distance. And if we simplify this particular equation, then we get equation number 8.52. So we if we put the value of omega t in equation number 8.51, we get the magnitude of the electric field intensity, which is equal to E naught into sine of k z. Okay, this is the magnitude of the electric field intensity, and you see this magnitude is changing with respect to distance only. Beta in this particular case is equal to k. So if we focus on equation number 2, the magnitude of the electric field intensity varies sinusoidally with respect to distance as well. If we plot the magnitude of the electric field intensity with respect to distance, we will get a sine waveform. So let us consider the waveform of the magnitude of the electric field intensity with respect to distance. So here is the waveform of the magnitude of the electric field intensity. We take the magnitude of the electric field intensity along a y-axis and kz along x-axis. So this is kz because we represent beta by k. So we get a sine waveform. You see the electric field intensity varies sinusoidally with respect to distance as well. And now the distance traveled by one complete cycle of the wave is known as wavelength, and wavelength is represented by lambda. So the distance traveled by one complete cycle of the wave is known as wavelength. So we want to derive another equation for the phase constant, and in order to derive another equation for the phase constant, we consider the value of kz at this particular point, at point P. You see, the value of kz at this particular point P is equal to 2 pi. So if we consider point P, then the value of kz at point P, the value of kz is equal to 2 pi radian. And we know that at point P, the distance is equal to the wavelength of the electromagnetic wave. So we replace z in this particular equation by lambda. So k lambda will be equal to 2 pi radian. So we get this particular equation, and from this equation we can find out the value of k. So k will be equal to, the phase constant will be equal to 2 pi divided by lambda. So we can calculate the phase constant with the help of this particular equation as well. Okay, what we need to do, we need to replace this beta by k, so we can calculate the phase constant with the help of the wavelength of the electromagnetic wave. So we can calculate the phase constant with the help of two equations. We can calculate it with the help of the wavelength of the electromagnetic wave, and we can calculate this k with the help of the angular frequency as well as the permeability and the permittivity of the medium. This is another equation for the calculation of k. So we can use any one of these two equations to find out the phase constant or the propagation constant of the transverse electromagnetic wave, the electromagnetic wave in any medium. Now we are going to derive the equation for the speed of the electromagnetic wave in any medium. We know that the speed of the electromagnetic wave depends upon, you see, the medium as well. We discussed this characteristics in our previous classes, that the maximum speed of the electromagnetic wave takes place in a free space only. In any other medium, the speed of the light wave depends upon the refractive index of the medium. So this is one way to calculate the speed of the light wave in any medium. But we are going to derive many equations in this particular class. We can use any one of those equations to find out the speed of the wave in any medium. So let us consider the equation for the electric field intensity of the transverse electromagnetic wave in a lossless dielectric medium, we consider the magnitude of the electric field intensity only. We know that it's a vector quantity, and it will have a magnitude as well as a direction. So we don't consider the direction of the electric field intensity, we just consider the magnitude of the electric field intensity. So the electric field intensity will be equal to E naught into sine of omega t minus k z. This is the magnitude of the electric field intensity in a lossless dielectric medium, where E naught is the amplitude of the electric field intensity in a lossless dielectric medium. So let us consider this equation in equation number 8.52 once again. Okay, so we consider the magnitude of the electric field intensity in a lossless dielectric medium. Well, beta in this particular case will be replaced by k. So this omega t minus kz is known as the phase of the wave, and we can show that the phase of the wave is always equal to a constant quantity. So the phase of the wave does not vary at all. It is also it is always equal to a constant quantity. So what we do, we replace omega t minus kz by a constant. So omega t minus kz is always equal to a constant. Okay, it is always equal to a constant. Okay, so if it is equal to a constant, so we consider this equation which is omega t minus kz, and omega t minus kz is equal to constant. So what we do, we differentiate both sides of this equation with respect to time. So if we differentiate both sides of this equation with respect to time, we get this particular equation where beta in this particular equation is basically equal to k, where k is the propagation constant or the phase constant. So omega minus beta into dz by dt will be equal to 0. And if we simplify, you see, this particular equation, then dz divided by dt will be equal to omega divided by k. Okay, we have omega divided by k. So this dz by dt will be equal to omega divided by k. And what is dz by dt? Dz by dt is the distance traveled by the wave, and the distance traveled by the wave per unit time is known as the speed of the wave. So if we want to calculate the speed of the wave, we can calculate the speed of the wave with the help of this particular equation as well. So this is equation number 8.53. So if the angular frequency of the wave is known, and if the phase constant or the propagation constant is known, we can calculate the speed of the wave in any medium. We know that the propagation constant is equal to omega under root mu epsilon. So we know this particular equation as well. Okay, so we know the value of k. So if we put the value of k in this particular equation, let us put the value of k in equation number 8.53. So let us put the value of k in that particular equation. So the speed of the wave will be equal to omega divided by omega under root mu epsilon. So if we simplify this particular equation, we get the speed of the wave in terms of the permeability of the medium and the permittivity of the medium. So the speed of the wave in any medium will be equal to 1 over under root mu epsilon. So we can calculate the speed of the wave with the help of the permeability as well as the permittivity of the medium. You see, the speed depends upon these two parameters. It depends upon the permeability as well as the permittivity of the medium. So if the permeability increases, the speed will decrease, and similarly if the permittivity of the medium increases, the speed will decrease. And this is why the maximum speed of the wave takes place in free space only, right? So this is another way to find out the speed of the wave in any medium. Now we know that omega is equal to 2 pi f. So omega is equal to 2 pi f and k is equal to 2 pi divided by lambda. And as the speed of the wave is equal to omega divided by k, let me call it equation number 3. So if we put the value of omega in equation number 3 and the value of k in equation number 3, we get another equation for the speed of the wave, which is given over here. In this particular equation, you see k is equal to 2 pi by lambda. So as v is equal to omega by k, so we put the values over here. We have 2 pi f, and then we have lambda divided by 2 pi. So we get this particular equation. So we can calculate the speed of the wave with the help of this particular equation as well. And you see from here we can derive the well-known relationship between the frequency and the wavelength of the wave. So the frequency is inversely proportional to the wavelength. F is equal to v by lambda. Okay, so now we consider the speed of the wave in any medium. So the speed of the wave can be calculated with the help of the angular frequency and the phase constant. And if the speed is known, we can calculate the phase constant with the help of omega divided by v. And what we do, if we put the value of v in this particular equation, because v is equal to c by n, so we get another equation for the phase constant. The phase constant will be equal to omega n divided by c. So we can calculate the phase constant of the electromagnetic wave in any medium with the help of the angular frequency of the wave, the refractive index of the medium, and c, which is the speed of light in free space. So we can calculate the phase constant with the help of equation number 1 as well. Okay, we know that the phase constant in free space will be equal to omega by c. Why? Because the propagation constant is equal to omega by v. So if it is equal to omega by v, and we know that v in free space is equal to c, so we can calculate the propagation constant of the electromagnetic wave in free space, which will be equal to k naught, and k naught will be equal to omega by C. So what we do, we consider these two equations. Let me consider these two equations for you guys. We consider K naught, K, which is equal to omega by V. And then we consider K naught, which is equal to omega by C. So if you put, you see, if I divide K by K naught, let me divide this K by K naught. So K by K naught will be equal to, we have omega by V and we have omega by C. So we have C by V. And if we put the value of V over here, we know that V is equal to C by N. Okay. So if I put the value of V in this particular equation, so we get the value of K, and the value of K will be equal to K naught multiplied by N. So we can calculate, you see, the propagation constant of the electromagnetic wave with the help of equation number 3 as well. We know that K is equal to 2 pi by lambda and K naught is equal to 2 pi by lambda naught N. So if we simplify, you see, this particular equation, we get another relationship. So what we do, you see, we get lambda naught, we get lambda naught divided by lambda, which will be equal to N. So the simplification of the previous equation gives you this mathematical relationship. And you see, lambda will be equal to lambda naught divided by N. And this is the relationship between the wavelength of the electromagnetic wave in any other medium and in free space. And this relationship shows that the maximum wavelength takes place in free space. In any other medium, the wavelength of the electromagnetic wave will be less than the wavelength in the free space. So this is the relationship between the wavelength in any other medium and the wavelength in free space. Now we are going to talk about, you see, another law which is known as Beer's law. So let us talk about Beer's law. What we do in this particular case, we consider a lossy medium. So this is a lossy medium. The input power is P1 and the output power is P2. And let's say the length of this lossy medium is L. So it is L meter. So let's say the total length is represented, the total length of the medium is represented by L. So we have Z is equal to 0 over here, and we have Z is equal to L over here. Okay. So at the beginning, Z is 0, and at the end of the medium, Z is L. Okay. So we know that the power is directly proportional to the amplitude of the electric field intensity. Let me consider the amplitude of the electric field intensity in this particular slide. So what we do, well, I don't consider the amplitude of the electric field intensity. Here is the square of the amplitude of the electric field intensity. So we know that the power will be equal to constant multiplied by E naught square into e raised to power minus 2 alpha z. So if you want to calculate P1, you see for P1, Z is equal to 0. So for P1, Z is equal to 0. So let us put the value of Z in the equation for P1. So we consider the value of Z for P1. So if I put the value of Z in equation number 1, P1 will be equal to constant multiplied by E naught square into e raised to power minus 0. Why? Because the value of Z for P1 is 0 and e raised to power minus 0 is 1. So P1 in this particular case will be equal to a constant multiplied by E naught square. Let's say this is equation number 2. For P2, Z is equal to L. If we consider the previous diagram, you see for P2, the value of Z is L. So we consider P2, and for P2, we will put the value of Z over here. Z in this particular case is L. So let us put the value of Z in equation number 1 to get P2. So if I put the value of Z in equation number 1, we get a constant multiplied by E naught square into e raised to power minus 2 alpha L. Now what we do, we calculate P2 by P1. So let us calculate P2 by P2, excuse me. Let us calculate P2 by P1. So if we calculate P2 by P1, P2 by P1 will be equal to e raised to power minus 2 alpha L, where P2 by P1 represents the loss of the medium. So we can calculate, you see, this ratio in decibel as well. So the decibel value of this ratio will be equal to 10 log of P2 by P1. And if we put the value of P2 by P1, we get this particular equation. Let me call it equation number 5. So dB will be equal to 10 log of e raised to power minus 2 alpha L. And equation number 5 can be written as, you see, equation number 5 can be written as, we have minus 20 alpha L into log of E. So equation number 5 can be written as, okay. So the decibel value of the loss, which will be equal to minus 20 into alpha into L into log of E. We know that E is basically equal to 2.71. So if I put the value of E and if I calculate the log, I get the decibel value of this loss in equation number 5, which is minus 8.685 alpha L. And definitely dB by L will be equal to minus 8.685 alpha. This is equation number 6. This dB by L is represented by gamma. So dB by L is represented by gamma, and dB per kilometer will be equal to minus 8.685 alpha. So we also know that P2 by P1 will be equal to 10 raised to power dB by 10. And if I put the value of dB, you see, if I put the value of dB in equation number 7, dB in equation number 7 is gamma L. So P2 by P1 will be equal to 10 raised to power gamma L divided by 10. And this equation is known as Beer's law. Thank you so much.